I'm no longer muted. Excellent. Hello, Eric. We will get started shortly. Fear not. Oh. Stream questions. We up. Hello, hello. Perfect. Okay. I'm going to go here. I'm going to share my screen. Excellent. Good stuff. Yeah. Wow. All right, we have some joiners. Excellent. Okay, close the window. Yeah. Oh, well, that's fine. All right. So I guess we can get started in that case. All set? All right. Hello. Thank you. Great turnout, like 10, 15-ish people. I'm sure a few onliners as well. And yeah, we're going to go through some reverse engineering and binary exploitation challenges. So the way I've decided to structure this is we're going to start off with reverse engineering because reverse engineering is going to be part of binary exploitation when we're actually taking apart the file, analyzing, and finding vulnerabilities. So we're going to start with reverse engineering, and I have two challenges for that one. One is fairly simple. You could just do it like purely just by looking at the file. The second one I've had to make harder for today because I realized during the event, after someone was messaging me, they realized that it was actually a lot simpler. And that's why I was getting so many solves, because people were literally taking it apart and they were just doing like the brute force action of going through every function. Yes, yes, yeah. And so I realized after I disassembled it after the event that the compiler optimized it and it was folding a bunch of the constants together so that there was less computation happening at runtime. So I fixed that. I made it much more difficult for you guys, and we're still going to solve it perfectly fine today. So in stream questions in the Discord, I posted a zip file. That zip file has all of the files, all the challenges that we're using for today. So I have it here on my desktop. I'm assuming you all have an environment set up to use for this already. So we are just going to unzip that, go inside, and inside we'll see we have 6 challenges and then this text file flag.txt. The reason flag.txt is here is because some of these programs are going to be looking for that file in the current directory. So I have it over here. You can see just some example data in there. So at least when we solve the challenge, we're going to have some output. We know that we actually did solve it. And with that out of the way, our first challenge that we're going to be looking at is TinyElf. So the name is a hint to what it is. So if we run file against it, then we see it is a ELF, executable linkable format, 64-bit, least significant bit, x86 64 architecture, statically linked, no section header. Basically, it's a program. It is a program, and it actually happens to be a very small program as well, 560 bytes only. So yeah, the name is kind of a hint as to what the challenge entails. And we can do a little bit more testing on this. I'm going to activate my virtual environment here, and we can run checksec on it, and we can see, okay, no relocation table, no stat canaries, no position independent execution. We're going to be talking about all of these things later on in the other challenges, but basically it's a very small file. It doesn't seem to be doing anything super crazy. So we can take it apart, and to do that, we are going to employ my most commonly used reverse engineering tool, Ghidra. So this is one of the things I've told you to also download, put in your environment beforehand. It doesn't take like super long to set it up, but you do need JDK, so there might be a little bit of setup there. And we are going to open up our file. So we have TinyElf. We are just going to drag it in to import it. Ghidra has already detected it as x86, little endian, 64-bit, built with GCC. Just hit OK, import everything. OK again. Double click it, open up the code browser. And we're going to have a look at what code is actually in this binary. And of course, it's going to take a second here. Okay, and Ghidra's already asking us if we want to analyze the file. We're just going to go ahead, say yes. Analyze, yeah, all the defaults are completely fine for this. We don't need to do anything too crazy. And you can see already on the side, inside this main listing over here, we have an entry point. And you'll see it's also a kind of a weird address. You might not recognize it as weird immediately, especially if you're new to reverse engineering, but you're going to see this is a very different address than the other programs that we're going to be looking at. In any case, we have this kind of attempted decompilation. It is doing, it's trying to decompile it as if it was a C program. And I did not write this program in C. So obviously it's going to have some issues when it's trying to fill in the patterns that it thinks it's recognizing, when in reality it doesn't. So we're actually going to mainly start looking at all of the assembly over here. Yeah, and you can see there's this pattern. We have a move, sub, add, sub, and between every one of those instructions we have call, and it's actually calling the same function over and over. So we can click that. Our decompilation is still very unhelpful. And this is the entirety of the function. There's an XOR, there's some move instructions, doing some stuff with the stack, syscall, and an exit. Cool. So we've had a look at it. It doesn't immediately look like a super malicious program, so we'll exit out of that temporarily. We will go back to our terminal, and we're just going to try and run it. And we get nothing. So did it even run? That is probably the next question. But we can actually see if we just try and get that exit code over here at exit 0.
So you want to explain what that $sign question mark is?
Yeah, the $sign question mark. That is a shell variable, and that just means it's getting the exit code of the program that was last executed in the shell. And by convention for Linux, 0 means it is a successful execution. So the fact that we got 0 here, it means that, yeah, we did run the program and we didn't actually have any issues with it. So let's go back to the code browser. Let's have a look, see whatever is in this program, and let's just start going it instruction by instruction. We know the entry point. It's right over here. So the first instruction being executed is JZ, or jump if 0. We're checking the flags. Welcome, welcome. Yeah, so the first instruction, we're checking the flags. We're checking if it's 0. Actually, we're not really checking anything, but we're just going to jump if the 0 bit is set in the flags register. And where are we jumping? We're jumping to this function over here. That will be useful a little bit later on. But if we look at the next instruction, now we're jumping if not 0. Well, if something is 0 and something is not 0, that accounts for every case that we could possibly have, right? So in reality, both of these instructions together might as well just be a single unconditional jump. We're not actually doing any comparison. So where are we jumping? We're jumping to this thing that Ghidra has recognized as a function. And it is 2 move instructions, a syscall, and then a couple null bytes at the end. The null bytes aren't super important, and we're going to see why in a second. This syscall instruction, this is something you might not have seen in our assembly classes. This is basically doing what that interrupt was doing in our assembly classes. It's reaching out to the kernel. It is trying to figure, or the kernel is going to figure out what we're trying to call, and then it will do the thing that we've asked it to do. And the way we do that is by passing in certain values as like keys for what we want the kernel to do. So we're passing in 0 in RDI, 3C into RAX, and hexadecimal. So let's
quickly, I know most people in this class.
Yes. So a register is basically just a very small piece of memory that's very fast. There's a fixed number of them in every processor. And on x64 systems, so most systems that are in your computers today, these small memory things, they typically hold up to 8 bytes. RDI, or any register prefixed with an R, means it's using up that full 8 bytes. E means 4 bytes. And then things like AX, BX, CX, DX, those ones are 2 bytes. And then there might be like high and low single byte registers. But generally speaking, we're going to be using the 8 bytes and the 4 bytes ones the most. So we have the syscall instruction. We want to figure out what is syscall actually doing. When the kernel receives this instruction, what is it going to try and do? So we can look it up. x64.syscall.sh. You can just Google for the table, you will find it. This is just a resource I like. It looks sleek, it looks cool. And we're going to look for 3C because that is the code that was in RAX. And we can see 3C, this corresponds to the exit syscall. And the argument it takes is the error code or the return code. So when we go look back at RDI, we see we're passing 0 into it, and then it's calling exit. So we've just exited the program with the code 0. And in reality, because we just had these 2 jumps at the start, we are just jumping to the end, exiting. That's all we're doing. We're not executing any of this other code. So the next logical step is, well, what if we did execute the rest of this code? All we really need to do, we just need to get rid of these 2 jump instructions, or we could change them to something else so that when the program loads this entry point, it will just start executing the rest. And that's exactly what we're going to do. We are going to go, whoops. Going to go to defuse assembler. This is just an online utility I like for quick and dirty assembly compiles, yeah. And we're going to assemble a no operation instruction. Yeah, we just need one code. So it's 0x90. And what we're going to do is we're going to look at these 2 instructions. We see each of them is 6 bytes long. And we're just going to replace all of these bytes with 0x90. So this is where your hex editor comes in from your bill of materials.
Also, no instructions, those docs, make doc slides for binary.
Yeah.
Use them in multiple things, not just reverse engineering.
Do this a bit differently. So here we are in the hex editor. We have our hex jump. I'm just going to close all of this stuff. I don't care about it. And we're looking for 0F8400. 0F8400, and we want 6 bytes. And then the one after it, 0F85FA, and then another 6 bytes. So we'll start over here, FA, and all of those bytes. Right click. And there should be something to replace fill. Oh, whoops. I did that wrong.
Where is it? Phil. Number of bytes or no? Okay, so we've replaced everything with our no op instruction. Going to save that. Both of them, yeah. So each one of these instructions was 6 bytes long. So we replaced 12 bytes to get rid of both of them. And we no, I don't want to save any of that. So we've patched the file. And we're going to verify that we've actually patched it. So in the hex dump, you can see we have all of these 90s all in line over here. And we're just going to run this. We're going to see what happens. We're going to actually execute the rest of the code in that binary. And it prints out our flag. So just like that, we don't actually have to go figure out what every instruction is doing. We just have to run the program.
And for example, people did do that. Yeah.
Yes.
Teams where they were one by one going through like all of the
Yes.
functions and finding out which things they do.
Yeah.
Writing out the bytes and then going, yeah, I have all the bytes in a word document.
Yeah.
Are they right? And Conrad's like,
Yeah.
I do it that way.
Like one team had a typo in one of them. They transcribed a 1 as a lowercase l or something.
Yeah.
And chaos ensued.
Yeah.
So it's like, so actually the next challenge we're going to look at is the one John's talking about. And I will show you because I just made it harder for you guys. And it'll be interesting, I hope. So we don't have to save. I'm going to save anyway. We can exit out of this. And the next challenge we're looking at is scrambled scroll. So it's this one right over here. And as per usual, we are going to do our due diligence. We're going to do our little scans on it. So, yep. At the very least, we want to see what this is. So in this case, there's even a build ID. It's where we're loading in the standard library for C, GNU Linux 4.4.0 loader, and basically everything else that we saw in the last program. So it's ELF 64-bit. Gonna run checksec on it. Okay, it has stack canaries. It has a non-executable stack. No position independent code. That's completely fine. And let's try running it this time around. Oh, okay. So we need an argument, and the argument has to be the flag. So let's just try something. Invalid flag. So for this challenge, we have to know the flag before we solve the challenge. And in order to do that, we're going to open up the binary again. So just load that into Ghidra again. Could be in the same project, doesn't really matter. The default settings for Ghidra are also completely fine. And open that up in the code browser and let's see what's going on. We'll hit analyze. Okay, it found our entry point. It's still doing all kinds of scans. Okay, we're done. So let's look at the entry point, and we have something kind of weird over here. Now this, again, if you've done reverse engineering for a little bit, you will know that the ELF format, at least if you're compiling it with a normal compiler like GCC or Clang, you're going to get this kind of entry point. And it's going to be doing things like loading global constructors. It might do other like Linux kernel libc things. So in our case, yeah, it's trying to invoke the start function, but it's going to be populating it with some other information that it got from the system. And if you've ever seen this piece of code before, you will know this first parameter that's passed into libc start main. That's the actual main function. So we can double click that. And we can go have a look inside. Okay, pretty big buffer, 0x2f, okay. We have that help string that we had. Param1, let's change things up a little bit over here. Let's rename this to argc by following the C main function convention. For this one, we will do char and rename, sorry.
rename this as argv. And now we can hopefully read this a little bit better. So yeah, we have our help message. argc is not 2, so we need 2 arguments to run this code. It is checking the length of the first argument that we pass in, because the 0th argument would be the name of the program. And if it is not 0x2f bytes long, which is 1 less than 48 or 47 characters long, then it's invalid. So we know that our flag is going to be 47 characters. It will exit, and then it will copy that, that argument we've passed in into some kind of local buffer, and then it will invoke this function on it. So what does this function do? Complicated stuff. It is referencing things in like static memory. It has more function calls. We can click through things. Oh, okay. So we've found some sort of exit condition if we have the wrong flag. That can be helpful. Well, what other kind of strings can we find? Go to search for strings. And what do we get? We get congratulations. So let's go to this string over here. And we want to find out what is referencing this string. What function is called to print out this string? Well, that's what this cross-reference message over here, that's what it means. It's saying that this function is making use of this string in memory. So we can double-click that. Awesome. So this is our exit condition. If we've gotten the right flag, we're going to print this out. What other functions do we have?
Just a few.
Yeah, there's a few functions here, and if you click through them, you're going to find a lot of them are of the same format. It's doing some XOR, it's doing some kind of dereference, it is taking in some other static memory, which you have no idea what it is, and yeah, it's weird, it's complicated, and I don't think it's going to be very fun if we were to solve this manually, right? Because I could do that live. We could just go through every single function. We can go up that cross-reference tree to find the correct path. We can go pull out all of those bytes. We can do the calculation ourselves. But that's no fun. We're going to be here for an hour. That's going to be really, really boring. So instead, we're going to automate it. And this is where a tool like Anger comes into play. So let's exit out of our code browser. We just keep in mind for now, keep in mind this string. It has the word congratulations in it, right? It's the only thing you really have to remember for now. And I am not actually live coding. For what it's worth, I do have a second screen over here with the correct code.
He's cheating.
I am cheating. But we're going to go through it. We're going to go through it line by line so you can see exactly what we're doing and how we're going to automate this process of figuring out what the flag is. So you can exit Dolphin and awesome. So we have this Python script solve.py, and we are going to use Anger for this. And Anger is one of the things I mentioned that you might have trouble installing. And you could only install it through pip, or you could build it from source. But you can't really install it at a system level. It makes use of all kinds of other things, and honestly, a lot of distros just don't support it because it is a fairly new project. But what Anger is, it's this framework for automating reverse engineering. So you can programmatically take apart binaries and do your analysis on them, and then it will do all that heavy lifting for you, and you just kind of reap the rewards with it. So we're going to start off, we're going to import Anger, and we're going to import another feature of Anger, another one of its like dependencies. It's called Clarify. And our goal is, we know what our success function looks like. We know what it's going to print out. We know where it is in the code. What we want to know is how do we get there? What kind of input do we have to give the program
to figure out to get that correct pathway. That's really the main idea that we're trying to solve. So we're going to start off by making a project for anger. And just as the name implies, yeah, we're just making a project. What do we know about the flag? We know it was 47 characters long. And we know another piece of really important information. We know that it's going to start with Fantasy CTF, squirrely brace, and it's going to end with a squirrely brace, because that's the flag format that we've given people at the event. Yeah. So, going to define that constant there. No semicolon. And for the actual characters, well, the characters are some constraints that we're trying to satisfy. So when anger is going to be crunching the numbers and looking at like that whole pathway of functions it needs to take, it's going to think of each byte in our input as a constraint that it's trying to solve. So this is where Clarify comes into play, and this is going to sound a little bit complicated, but BVS format string. So this code itself, it's just a list comprehension, right? We're making a list and we are iterating from 0 to 46. And for every number that we're iterating over, we're making a new constraint. A single 8-bit value, and is a bit vector. That's what Clarify calls it internally. So 46 characters that are 8 bits long. And those are the collection of constraints that we're adding into this. This, a little bit of weird Python stuff, that star, it's basically exploding that list and then passing every element of that list into the function. So it's 46 parameters that we're passing in. And we're telling Clarify that our flag is going to be a concatenation of all of those bytes together. And now, like I said, we know the prefix of the flag. That was the prefix we had. Why did oh, there we go. And because these are the known bytes, then we want Clarify to see that it doesn't have to change those bytes at all.
What about the final sort of
We will add it. So the thing is, you don't actually have to add in all of this information. You could just brute force it. But it's just we are speeding up the process a lot because we exactly. We're just trimming down the actual computation that we're taking for any of this. Okay. So we need to make program state. And this is through anger. Oh.
I guess if people were making this program from scratch, they could look at like the man page for anger.
So actually, yeah, not only the man pages for anger, but there are examples online that you could pull from that will do exactly this. That will also just like you can pass your like flag as a parameter. I'm doing this live so I can explain it line by line, but yeah, realistically, like you could very much Google this and find an example script online. So we've created our state and we know that anger is going to be running this program with the constraint as the argument. No, whoops.
This has to be a byte array. My bad.
How new is Anger? I haven't heard of it before.
It's I think it came out like maybe 2 years ago, or it really started getting its like stable releases. But it is a very useful
It's
tool.
extremely.
It is. It uses Z3, if you've heard of that, like underlying for the symbolic solver, which is what we're using right now. And as you mentioned, we need to add that last
Right.
squirrely brace to it. So state.solver.add flag chars -1 equals. Cool. Okay, so we've created our constraints. Now we need to define what success looks like. And this is just going to be a function, and we're just going to say we've succeeded when we have some kind of output. And the output that we are looking for is congratulations. So we will just put in out equals stuff politics dot dump s from standard out.
So I guess if you would pass like what 2 or 0 in there, or different standard error or something.
Exactly, yes. And we're just going to see if congratulations was in our output. And this is a function that we're going to pass in to Anger as well, so that it can be running this check over and over and over to make sure that it is getting the correct output. All right. All right. Oh, that is not correct, that line. Okay. We've done all the boilerplate. Now we just have to let Anger do its thing. So, sim gr.
With that last line.
Sort of.
You're just passing stuff in, basically.
So we have a state, right? We've created a state where we know how we're calling the program. We know the constraints. We know some values of the constraints. And now we are just loading that state into the project. I don't exactly know what that acronym means. I will.
That's all I was just checking.
Yeah.
Just because I see you putting in a line, but that's the first line so far that you haven't actually said a name of.
Yeah, I don't recall what the SimGR is. That would make sense. Yes. Okay. Yeah. Yes, that would make a lot more sense. Yes. And this last line, explore, it's just telling Anger to go do its thing.
Is that an equals?
Yes, because we're passing success, the function that we've created.
Oh,
And we're looking for that.
yeah.
That's our success condition. So that's what we're looking for. That's what we want to find. And Anger can go do its thing. And now we just have to print out whatever we found. So if simulation manager found. I will explain all of this shortly. Okay, that is the entirety of our script. So if we have found a solution with the constraints that we've given, then we will grab that first solution in the list of possible ones. Then we're going to cast it to a bytes object. And then we're going to decode bytes to ASCII and then just print that out. That's all we're doing. And if I have done this correctly, that did not work. Was it because I didn't save? I think so. So it takes a second. It has to compute it. But it found the correct way to get to the function that we wanted it to. It satisfied all of the bytes, figured out whatever the actual constraints needed to be, and then it just printed out our result, just like that. And it really does feel like magic because none of this code even feels like we're trying to reverse engineer anything, right? Everything that we're doing is almost like this really indirect way. We're more concerned about like the constraints. We're more concerned about anger itself. It doesn't even feel like we're attacking the binary. The only reference to it is like right up over there for the project in the entry state. So yeah, the fact that we're able to leverage anger to just spit out the flag for us, we can be diligent as well. You know, we can go look at a, you know, I'm going to exit all of this. Gonna run this again, give it a second. And yeah, we're diligent with it. We can verify that we got the right output. Sure enough, we get the correct pathway. We figured out the flag before we even solved the challenge. So that's it for Rev. The other challenges won't be so complicated, or at least early on. So what are we at? We're at 549.
That's pretty
Okay, cool. I'm gonna go grab some more.
good. Yes.
So yeah. I'll leave you open. There we go.
Stream. Yeah. Looking at my phone. Why is it so slow? Oh, yeah, that's why. Is it? Oh, yeah. 68. Yeah, no, this one's huge. This one's volume information is 20. I can't do anything. This is Cali. It's the type. This is like most of my computer right now. I mean, I could lower my colors. I think it's less. I think it's like
All right, hackers, we're back. All right, back to our files over here. The next challenge we're going to look at is words of power. So this one is a much simpler binary to take apart. We basically just have to load it up in a Ghidra and we're going to see everything that we need to see. So that's exactly what we're going to do. We are just going to import it. Where is it? Words of power. And as per usual, open it up in the code browser, hit analyze, use the defaults. And this time, instead of an entry point, we have a main function. So we could just go there instead. And okay, we have more of this kind of buffer stuff again. We're printing out this message, enter the first word of power. Then calling this getS function, this archaic thing, and then puts, enter the second word, and that's about it. And then we're comparing both of these strings. So the first one's being compared against Salvus, the second one's compared against Silente. And if both of those words are correct, then we get the flag. And as you can see, this is catflag.txt. So this is where we do want that like temporary flag.txt file in our current directory. But if you've noticed, we only have this weird getS function. We're not using scanf or fgets or anything like that, getchar. What does gets do? That's not what I wanted at all. And we can use this one. cppreference.com. It happens to have a lot of C functions as well. Should not be taking this long to load, but yep. Or maybe just my computer, I don't know. Let's race it with something else. Okay, well, we're here. We are reading from standard input into a character array pointed to by str, and str is the parameter inside of it. So based on that, we can go look at local 38, and we know that this is going to be input instead, and we know it's of the type character array. So let's rename that to input. And then back up over here. Oh, well, okay, awesome. We've recognized it as a character array because it was being used by gets over here. At least it's a little bit more readable for us. We don't have this like local plus address combination. And it reads until a new line character is found or until an end of file occurs. A null character is written immediately after the last character. The problem is, it doesn't mention it over. Oh, I guess it mentions that it was removed in C11. There's no bounds checking. It doesn't take a length in. So even though our buffer is, what, 32 bytes large, goes up to 1F from 0, yeah, 32 bytes. And it will read a lot more than 32 bytes if we let it. And the thing is, because both of these, I guess, well, you can see it's kind of ordered weirdly. We start at 0 in the middle over here, go down, and then we go up to 0x10, and then down to 1F. And yeah, okay, we can look at our stack frame. We see it's stuck at a 0x38 over there. But if we're starting at input over here, so we're starting halfway down the list. Oh, okay, actually this disassembly is really weird.
Say, go
Yeah.
and then to be.
Yeah, okay, yeah, so it's a little bit weird. When I was distributing this challenge at the event, I gave a source file. It was a little more obvious what was going on. I don't think I can pull it up right now. I don't have all the challenge file. Maybe I do. Maybe I do.
Oh, actually, I think I do. Yeah. Okay, so this is what the actual code looks like over here. Sorry about that. We have two character buffers, word B and then word A. And you could see actually the second call to get input was commented out. And yeah, without the capacity to enter input the second word, the party will never open the box. So we need to find out how to get data into word B so that we can actually exploit the system. And because get s doesn't do any bounds checking, it's going to read into these 16 bytes. And then if we give it more than 16 bytes of input, then it will start reading data into word B as well. So we can test that. We can go back. There. Okay. Words of power, we can do solve a lot of A's, silente, something like that. And it doesn't work. That's, again, irrespective of if I had the offset correct and all of that. But we can't just use any normal character because those A's are still interpreted as part of a string. Remember, the function that we're using to compare the strings is str compare, string compare. And what string compare is doing, it's doing a byte by byte comparison of every character in the buffers that we give it. So in the first buffer, it's our input. In the second buffer, it's this hard-coded string literal salvus. And it's doing that byte by byte comparison, and it only knows when to stop when it receives a null byte at the end of it. And we haven't given it a null byte, we were only giving it A's. So when it reached the null byte in the string literal, and it saw an A at the end of the first word, then it knew there was something wrong, it didn't match, so it exited, right? It stopped glowing, congrats, you break the seal. Okay, so we can't do that. We need a way to pass in null bytes into this program. And that's where we're going to start using another tool that I've told you to get installed, Pwn tools. So one of the first things we have to look at, the security. So Pwn check sec, words of power, and what do we have? No pie, no canary, executable stack, a lot of really, really bad insecure practices. Stack canaries are in one other challenge. Position independent code just basically means that when we're compiling the binary and when it's going to be executed and it's loaded by the operating system will figure out where to put certain functions in memory. It'll try and randomize the order so that jumping around between the functions is a lot more difficult. Executable stack. So we don't want the instruction pointer, the actual thing like reading and decoding all the instructions. We don't want it to ever point at the stack. We don't want it to execute user-given data. In our case, we're saying, though, it is executable, so we could do that if we really wanted to. The binary is not stripped. That means we can see all of these symbols. So we can see that this function is strcmp. We can see the function above it is puts and gets. We can see all of these things because the symbol table in the binary is still intact. We can see all of these names. Unlike the last challenge we were looking at, where everything was like fun underscore address, that's when the binary was stripped. We did not have those symbol names. So we had to kind of rely on our intuition to figure out what was going on. But over here, we can see everything. That's great. And we are going to write a new script. So first thing we're going to do, import Pwn tools, or rather we're going to import all the top level objects from Pwn tools. And we are going to make our target the program itself. Okay. Now, what do we want our payload to be? Ideally, we need it to have the words in it. We need those words to be 16 bytes apart, or at least the starts of the words. We need each word to end with a null byte. And that's basically it. That's all we really need. So we know that getS is going to put a null byte at the end of the input that we give it. So we don't have to do anything after we put in silente. But we do need to do something after solvus to stop that string compare input, or that actual comparison, and we need it to read like just that word as a single string, and that's it. So it makes sense that we just fill in that entire block of data between solvus and between silente to be all null bytes, and that's what we're going to do. We're going to define our payload as the byte array solvus, and we want to fill in the next 10 bytes because it's a 16 byte offset. Okay, so 10 bytes have been added on. So our total payload is solvus plus 10 null bytes for a total of 16. Then we are going to add in the next word as a byte array. And we can actually leave it at that because, as we've said, getS is going to append a null byte to this anyway. So we're just going to send that payload to the process in standard input. And target.interactive, it's just going to open up that I/O port between us, the user. So it's not going to be behind the script anymore. It's just going to be something that we can interact with. We can read all of the output from it. We can give input to it if we need to. This is going to be a method that we're using basically to finish off every exploit that we write. So save that, open up a shell, and just like that, we were able to get our example flag. It read from flag.txt. As you can see, it is not actually printing out what we've sent to it, but it's implied. This is just reading whatever the Pwn tools got from standard out. And yeah, we were able to exploit the binary. So when you're given a challenge for binary exploitation at a CTF, making your exploit and solving everything, you're not going to get the flag just by doing that. Usually that program is going to be running on a server somewhere else. And the idea is if you can break it locally on your machine using the binary that is given, then you should be able to break it across a network because you're just sending bytes to a different place instead of to a process on your computer. So because we were able to solve it over here, in theory, we should be able to solve it at the actual event. So yeah, sorry, I don't have the actual flag for this with me. It's somewhere buried in our repository, but that's the idea. We were able to break this application. We were able to put data where it shouldn't have gone. And as a result, we were rewarded for it and we got our flag. So that is perhaps the easiest binary exploitation challenge I had. We're going to go one step up from that. Okay, clear that. So the next challenge is going to be exam. This is another executable linkable format, 64-bit, yada, yada, yada. We've done this before. We already know what we're going to expect. I've told you all before that, like, yeah, all of my challenges are written on Linux. They're all Linux executables. Just work with that. So let's try and run it. What do we get when we run it? We get this output. We have this hexadecimal value. It says good luck. We could put something in there, hit enter. We don't get anything out of it. Let's take it apart. Let's see what the code is doing. We're here, import exam, and open up the code browser. Analyze defaults as per usual. And again, we have a main function. And here's that print that we had before. It is printing a pointer. We can see that by this format string over here. And what is it actually printing? Well, there's this thing called win. And win, when we double click it to see what it is, we see it's actually a function. And all it does is it looks up flag.txt in the current directory and it prints it out. So ideally, this is what we want to execute. But we have to do it a little bit differently. As you can see, we have this main function, and the only way it's even being referenced is by an address. So we need to actually redirect the program so that it will execute that function, because the program isn't calling it in any meaningful way. Now, like I said, it's only one step up. We have that same function over there, getS or gets. So we're reading in an arbitrary amount of data, and we have this buffer over here that is 32 characters large, I suppose. I don't know, this output looks a little bit weird, but I wouldn't worry too much about it. We have this buffer, and we can see that it is 0x28 bytes away, or offset on the stack. What do we know about the return function, or the return keyword? If you recall at all from your CPU architecture class, if you've taken CPU architecture, return has a very, very strictly defined function. It pops data off of the stack, and it puts it into the instruction pointer. So what we're doing a stack offset, and we're doing a move at the same time. And because we're popping something into the instruction pointer, we can control what the next instruction in the sequence of that program is going to be. Well, the return address is stored on the stack. And as I've mentioned before in one of the earlier challenges for Scrambled Scrolls, main isn't necessarily the first function that's called. In fact, it's going to be called somewhere along the chain after all the global constructors for the system are invoked. And it won't be the last thing to execute because the global destructors are going to be called afterwards. The system's doing all kinds of internal stuff. Main isn't your actual entry point. So when we're returning from main, we're actually going somewhere else in the program. This return is very, very well defined to actually have a function. And what we want to do in this case is we want to weaponize this return so that we're not going to return to the regular program. We're going to return where we want to go. And where we want to go? We want to go to win. So we'll go back. And as we know, where's main? There. We know that this buffer is stored 0x28 bytes away from the return address, which is right above. We know the return address is 8 bytes large because this is a 64-bit binary, as we were looking at over here. So we can start writing our script. We also know the address of win, so we know what we want to replace that return address with. So we're going to make a new script. We are going to import pwn tools, or rather import all the top level objects. We're going to make our target and we can start working on our payload. We could put in any kind of data into that buffer. If we go back to the code over here, we see we're not really checking what that data is. So it could really be anything. In my case, I guess I will just start us off with the byte capital A. And how many of them did we need? We need 0x28. You could do the conversion for that, but Python will also just let you define it literally as a hexadecimal value, just prefixed with a 0x. And now we need our return address. Well, we know the return address was being printed out I don't have it open over here, but we can even see it inside of Ghidra. If we just go to win, 401156, and that is a hexadecimal number as well. So if we keep that in mind, we're going to use one more function. We want to turn 401156 into a little endian number. So we want that 56 to be at the front. We want the 11 to be the second byte, 40 to be the third byte, and then a bunch of null bytes after it. PwnTools gives us a function to do just that. And it is called pack64, and we give it the number. The number we had was 0x401156. And then we'll just send our payload to the program. And that closing method, or that closing function I mentioned before, target.interactive, so that we can actually start looking at that output and interacting with the process. Save that, open up a shell. And there we go. We've got an R example flag printed out again. The program stopped afterwards, exit code 0. Okay, perfectly fine. End of file. So yeah, I mean, we can't interact with it anymore, but we got our flag. We were able to redirect control of the process by overwriting the return address so that when main finished executing, it actually went somewhere completely different. So that was one step up. Unfortunately, the next two challenges I do have planned. I can get through one of them for sure, but this one's going to be a pretty big jump. So I realized this shortly after. There could have been some more kind of intermediate stepping stone sort of challenges. But I think for the last one that I'm going to do, I want to highlight why this return address overwrite is such a big problem. I don't know if any of you know this, but the move instruction, the very primitive move one piece of data somewhere else, that instruction alone is Turing complete. You can represent any program you possibly could want using just move instructions. And in fact, there are tools online which you can plug your program into, and it will spit out the equivalent program in move instructions. It's brilliant. It's insanity. But you can do that. So this idea that all a return is doing is it's moving data somewhere else and then changing execution order, that's extremely powerful because that implies that we can actually write programs just by using return instructions and a little bit of data. And that's exactly what we're going to do. So the last challenge that I'm going to go through today, after I exit all of this, it will be time's ticking. So, see, it's the exact same type of file format we've seen before. And there's one kind of different thing about this program. I don't know if you can tell immediately just by looking at that output.
Quite large.
It is a very large program. It is almost 800 kilobytes. It's almost a full megabyte. And I can promise you, when we're going to look at the code for this, it's not going to look like a megabyte. But the difference is that when we run file, you see this one is statically linked. So the entire standard library for C, all your functions like printf or puts or system that we're using in all of these, all of those functions are packaged into this binary as well. And because they're packaged in, it's making our file size absolutely massive. But that also means we have a lot more code to play with now as well. We don't just have our little 16 kilobytes or whatever that was available to us before. Now we have the entire C standard library at our disposal. So that's what we're going to be working with, and we're going to import that into Ghidra and have a look. I believe this challenge was only solved by one other team. I think it was one of the McMaster teams at the CTF. So huge props to them. I think they got it done at like 3:30 p.m. on the second day or something like that. Like they were grinding it out, but they managed to get it done.
Yeah.
So we'll import it, all the default options, open it up, analyze it as per usual. We have a main function, so that is usually a pretty good indicator that the binary is not stripped in any way. So we still have that full symbol table at our disposal. We could see where all the functions are. And yeah, you can see it's still crunching all kinds of numbers. It's taking a little bit longer because it is such a big binary. So Ghidra is still working through it, trying to decompile all of the code in here, which is absolutely massive.
It's on printf when you say.
Yeah, yeah. Yeah, all the internal like standard library stuff as well. But okay, yeah, you can even see, oh, perfect. Okay, so as it's analyzing it, it figured out, okay, there's some strings over here, so we're going to populate that as well. But you can kind of see what this program is doing just off of the main function. There's this set sig alarm, armit, defuse me, 2 put statements, and an exit. So I don't think we can really do a whole lot with main, but we can have a look at what the other functions are doing over here. So the first one, set sig alarm. This weird sig action type. We are setting some memory to 0. What's this explode thing? You can double click that. It just prints a message and then it exits with a failure code of 1. As we mentioned, 0 indicates success, so this means we failed in some way. Okay, so there's some kind of handler, and it is invoking the sig action function, and we can go look up the table for this. We can go look up the man pages. I will just tell you off of what I know so we don't have to waste too much time. Sig action is basically a way to define how you're going to handle a signal. So let's say I'm running a program and I want to stop that program. I might hit Control-C to interrupt it in some way, and that will like close the program. Well, I can use sig action to change that behavior. So instead of Control-C exiting the program entirely, maybe it's just stopping like a single subroutine or a single function, and the program is still otherwise running completely fine. So what we're doing over here is we are changing the default behavior of the signal for an alarm. And an alarm is a way to automatically kill a process. Let's say if it's taking too long to execute. So if it takes more than 5 seconds or something like that. Okay, so this function is just setting that default behavior for how it's going to handle the sig alarm signal. Then there's this armit function. You can see it is setting an alarm for 1 second. So we have 1 second to exploit this program. Go back, and now we have this function over here. Okay, prints, cut the red wire. It sleeps for half a second. This is in microseconds. But first, and I don't know if any of you have seen MASH, the old TV show. This is a reference to MASH. There's one episode where they're trying to defuse a bomb. So they have this tape playing of like a bomb defusal instruction. So he says, cut the red wire. They cut the wire. But first, right? And then, yeah. So that's a reference to that. But in any case, right after, we have a call to read. And read reads bytes into a buffer. Very simple function. It's what things like printf or getchar or whatever, that's what they're using under the hood. They're using some form of read. And we're reading it into this buffer, local 408, and we're reading 2,000 bytes of it. And 0 is the file descriptor, standard in. So just by us typing things on our keyboard, that's how we're providing input to this function. It's putting in the local 408. This isn't entirely correct. As you can see, Ghidra has misinterpreted this data type as an 8-bit value. So we are going to change that instead to a character array. Oh, it did not like that, did it? Yeah, it really did not like that. Okay. Let's try a character pointer, maybe. Okay. That's not exactly what I wanted, but that's good enough, I think. Because the thing is, when we look over here, we see that this buffer is 408 in hexadecimal away from our return address, the thing that we were talking about earlier. If you do this conversion, I think it comes out to be like 1,000 bytes off the top of my head. I could be wrong about that. But basically, we have a buffer of 1,000 bytes, and we're reading 2,000 bytes into it. So even though we're not using like a unsafe function in any way, we have an overflow anyway. We have a way to write data out of bounds and then hopefully alter execution of the program in some meaningful way. So I would test that, but I would have to put in over 1,000 bytes just to get a crash. So I'm not going to do that. Like I said, this is only one solve. So I will just kind of go through the solution and we're going to gather a little bit of information. One of the first things I want to draw your attention to is the syscall table again. So as we've mentioned before, the syscall table is a way to make the kernel do things for us so that we don't actually have to write any crazy code to do things ourselves. And one of the more useful syscalls in here, I'm just going to Control F for it. I cannot type, is execve. Right over here. And what execve does is it loads a program into memory and it executes it. So it's how the shell is doing execution every time you type in a program name. It's just calling out to execve. And as you can see, we can pass in a file name, we can pass in arguments if we want to, and we can pass in environment variables if we also want to do that. And it is the code 3B. So keeping that in mind, let's start writing some exploit code for this. So this one was 3B. Okay. Do we need Ghidra still? Yeah, it could be useful. Oh, we also know that we need 400 or 0x408 bytes of data to get to the return address. So we can write that in as well. So everything after the 408 is going to be our exploit. So we can start off by defining our payload as just filling in that buffer just with random arbitrary data. In my case, I'm using an uppercase A. And well, we don't really have a win function in our case. So we have to build one ourselves. We know that there's a flag, and it's going to be on that server because there's no other mention of the flag in the code that we were looking at. There's just that diffuse me function. There's that sig action function to handle it. And then we're setting that alarm. But that's about it. Like, all we really have is this diffuse me function. So we have to build the code ourselves. We're going to be building a program within those return addresses. And this is something called return-oriented programming. So we are going to employ another utility. And this is another utility from PwnTools, actually. Actually, I don't know if it is. Do I have it installed? No. Cone tools does come into play as well a little bit later, but we're going to use something called ROP gadget. And what ROP gadget is going to do, it's going to look for certain patterns of instructions. And it's not only going to do that just like by the straight disassembly, it might look for specific patterns of bytes that are in executable memory. Because let's say a memory address that is being referenced in the code has the bytes 0f05c3. Well, that would be the instruction for syscall ret. So we could still use that as executable code as long as it was within executable memory. Okay, so as you can see, it gave us a lot of output, and a lot of this code is probably not going to be useful for our purposes. So we can start filtering things out. We can just pass it into grep, and we want to control the RAX register, because RAX is going to have the code for our syscall that we want to make, for instance. So we can go search for, I should really just have this like over here. Okay. Pop RAX. This was not good. Okay. Okay, so now we've searched for things and we've found some interesting instructions. This one looks the most promising. We have a single pop and it's followed by a ret. So we know that ret is doing a pop of some sort. So if we pad this gadget, as we call it, this little piece of code, if we put that address onto the stack and then we put a piece of data after it, when that executes, it will take that piece of data and it will put it into RAX. So let's keep that gadget known to us. 41E F84. Okay, that's one of them that we're going to need. execve needs 2 arguments at least, right? We need the second argument, which is the file name. We don't necessarily need argv, so we don't have to include it. We could just set that to 0 if we really wanted to. Same with rdx. But yeah, so we see where we have to put the data in. So we need to control RDI, we need to control RSI, and RDX. So let's do the exact same thing. Let's search for RDI. And we have a decent candidate over here, pop RDI ret. So 402 EED. We will do the same for RSI. It's another register we want to control. 402 EE9. And the last one, RDX, not to be confused with RDI. They are different registers. And we can see 402 EEB. Now you might notice these addresses are very close together, these last 3. 402 EE something. The reason that's the case is because I actually did include these specifically for the challenge. When I was actually writing my own solutions and figuring out how this is all going to work, I found there were no really good candidates for these gadgets that we would need. So I just decided to write them in inline assembly so that they were given to anyone trying to solve the challenge. Now, we need to pass in a file name, but that file name isn't anywhere in our binary. So we need to put it there somehow. We need to put it into memory, and we could do that by, for instance, when we're writing all of this data into that buffer, we could put it into there. The problem is if the system is using a technique called ASLR, and ASLR will randomize where that data is actually going to be in memory. It's going to randomize the address, so we can't actually predict where it's going to be. So we can't put it into there. This is going to be a little bit of a weird technique, but we're going to debug this application. So GDB, and we are going to start execution right at the entry point and then stop. And you see we have this kind of weird output. And this is something from GEF, the GDB extension framework, I think it's called. But we can see all the data on our screen at the same time. It is a little bit overwhelming at the start, but basically we can see all of our registers, the general purpose ones. We can see the stack frame and what is on the stack and all the different addresses. And we can see the instructions that are going to be executed. In our case, though, I'm more curious to see what kind of memory does this program have access to. And GEF, it gives us this cool command called VMMap, so virtual memory map. And VMMap will show us all of these regions of memory that the program is going to have access to, and it will tell us what can it do with that memory. So for instance, this section over here, 401,000, it has read and execute permissions. This is where the code is actually going to live because that's what's being executed. And you can see it doesn't have write permissions, so we can't change the code as it's executing. But we can go down over here and we have this, this section, 4A2000, it goes up to 4A8000, and it has read and write permissions. So we can actually write to this memory over here. And that's kind of cool. So let's take note of that. Writable chunk, and it starts at 0x4A2000. And let's give it some offset somewhere in the middle of that memory, just in case we're going to be breaking something. Maybe our buffer is stored there. We don't really know. But let's give it an offset of like 0x2000 bytes. Something like that. We're somewhere in the middle of the memory. We're going to write some data there. Now we need a way to actually put data in that memory location. So let's go back to ROP-Gadget. So we'll quit out of GDB and we'll run, you know what, let's go up. Instead of pop RSI, let's do something like move. And because we want to move something into a memory address, let's use the Intel syntax, open a square bracket that indicates a pointer. And we'll search for that. Oh, do a backslash on that. Hopefully, oh, it didn't like that. Okay. Well, let's just search for move then. Oh, that gives us a lot of data. So I'm going to filter it a little bit more. I'm going to say I want move to be the first instruction, and then we can look through that instead. Move ZX, that's not super helpful. Let's just try and find a raw move instruction. Here we go. Okay, well, we can move word pointers. Well, a word is only 2 bytes. We want something bigger than that. We want something that's going to hold that entire string for us, that /bin/sh. We want to make a shell. So scroll up and let's find something that's a move quad word. Have to go all the way up above the registers over here. Oh my God, there's so many. I'm going to do this differently. Okay. If we have our string /bin/sh in RAX, and we have the address in RSI, we can write /bin/sh to that memory location using this instruction over here, and then we return. So we'll take note of that address as well. And as you can see, all we're really doing, we're just finding these little atomic parts, and we're going to be putting them all together to make a full program. So the address for that one, 421B65. And now I'm going to need help from my write-up. And there is a function I wrote that will convert that /bin/sh into the correct format that we want. Okay, so I'm just going to try copying that one over. Okay, this function, it has a little bit of weird arithmetic. It's doing a bit shift. So it is encoding whatever bytes I give it. Or no, it's going to encode a string as ASCII bytes, sorry. And then it will try converting that string into a number. And it's going to do that by shifting it by 8 bits, moving that character or that byte into that 8-bit void that we've created, and it's just going to keep doing that until we have a number, and then it's going to spit that number out. That's all it really does. We're going to pack that later on. And okay. There's one more instruction we need. We need to actually invoke the syscall. So last search, I hope. Now we can start creating our payload. So we already have our buffer filling payload. Now we're overwriting the return address. So the first thing we want to do, we want to move bin sh into that writable chunk of memory. So and of course, we have to pack this as a 64-bit number because that's what's going to be pushed into the instruction pointer. What do we want in RAX? We wanted the actual value of bin sh. So bin sh. Okay. Gadget 1. Pop RAX. So the thing that comes after RAX is going to get put into RAX. That is our string converted to a number. The next gadget is going to be pop RSI. That's where we're putting in the address of the writable chunk that we found with GDB. The next gadget is just going to be copying that data into memory. Now we can actually start writing our syscall. So payload plus equals that was our code. So we're putting that into RAX. Second value we need is RDI, and that is the actual string. 864 pop RDI. And we already know where we put that, so we just use the same address again. Next thing we need to set RSI and RDX to 0, because those were arguments that are still being taken in. We don't want them to pollute our output in any way. So pop RDX. Okay, so we have set all of our registers. We invoke the syscall. We're going to send that payload, and then we are going to go interactive with it. That is the end of our script, and hopefully oh, it is not payload, it is target. And I don't recall if I even made a target. Yeah, so yeah, okay. So we'll do that up over here as well. And the name, there we go. Okay. Oh, and we have a problem. This is this is a little bit embarrassing, but what we can do it is there. No, there's something off with the exploit chain, but honestly, I think it's good because we have an opportunity to actually view the exploit chain in motion. So what I'm going to do is before I send that off, I'm going to run pause. And this is another Pwn Tools feature. It will pause the program itself as well as the script. And that will give us time to attach a debugger to the process, and then we can start visualizing everything that's going on. So one more thing before I do that, I'm just going to have a look in Ghidra. I want to see where this function returns. So it's going to return at 402 FDA. We'll keep that off to the side over here. Okay, we've paused. We have our process at 14,661. Okay, I will try and do some extra work over here. .402 FDA. I will hope that this works. I may have to Google for this one.
So that area you just had there.
Yep.
Says at first because you're trying to focus on my method on there, but it's turning not value with value.
Yeah, I know that. That's what the error code says. Oh, okay. Here we go. And did it pause? It did not pause. So, and it received SIG alarm. Does that mean it ended? Or does that mean that? There was a way to do this. I remember. Yeah. Okay. So.
Yeah. Oh, I watched some right there. No, I just did the reading. I didn't do anything else. Yeah, it's kind of interesting. Like it's supposed to
theories that we're living in a simulation and we are living in
It's a really interesting profit.
it's still you're gonna go independently. What's moving? No, it's like some philosopher has a proof. Yeah. That it's like, it's the chance that we're not living in a simulation is like negligible, so we must do. Yeah, yeah, it's like the philosophical proof of this, which is. I think appreciated. Like there's a lot of math, so like he tells us like the math part is not in the required reading. But if you actually look at it, it's like a lot of assumptions. Yeah.
I was bored while you were doing this thing, so I added a better scoreboard to the scoreboard.
Nice.
George sent me all the data for the CTF, so I'm just gonna like post it on my domain after all the static data.
Mhm. Yeah, I got nothing, honestly. Yeah,
Pretty solid. Solid.
honestly, it's just because I can't seem to continue the script while GDB is running, and I need GDB running
Yeah, the same.
to view what's going on inside of the script. Yeah, literally. There is a way to continue it executing. I've had this problem with it before, though.
Yeah.
So I have no idea how to like deterministically fix it. The way I've always done it before is I would just do pause, get the PID, attach GDB to that PID, and then continue normally. But yeah, if I'm doing it from within the script, which I have to do because the alarm is timing out the program, then yeah, unfortunately, I am stuck at this. But at the very least, this is at least a demo how you would try and write a program using only return addresses. And this entire kind of subfield of exploitation is called return-oriented programming, or ROP. So I hope at least that was a little bit enlightening in terms of how to exploit binaries, how to take them apart, how to automate decompilation, disassembly, how to read the disassembly, how to make sense of it. And yeah, I guess we'll call it there then.
Yeah, solid. Thank you.
Demos.
Yeah.
Eric praises you for your teachings.
Yes.
Saw that.
Yes.
And I'll leave a note that in the middle of the black screen, so you can cut it out.
Yep.
That could be done with something.